taking inspiration from the human mind to build a robot that could be possibly one day conscious. So before starting with my presentation, I will try to give you a very brief overview of some of the activities that we have in our laboratory. One project that we have from 2004 to 2007 is a project for a robot offering tours, guided tours at the Archaeological Museum in Agrigento. At that time was a very interesting experience, and because it was the first time that our robot went outside the laboratory and go into the real museum with real people, with real tourists that interact with the robot. It was a very interesting experience for us. And another interesting project was the more or less similar project offering guided tours at the Botanical Garden of the University of Palermo. It was very interesting because the robot was outdoor, and you may understand that going outdoor for a robot is a real mess, it's real complicated, and especially in a botanical garden where everything is not fixed. And another project is, I'm going very fast through some of the projects in our laboratory. Another project was the project related with the Puppet Museum in Palermo. There is a long tradition in puppet in Sicily, in marionette, in puppet. And so we had this very interesting experience of a mini show with a real puppet and our robot and our robot. So the robotic marionette and the real marionette. It was an interesting experience. We have a tight interaction with Osaka University and with Professor Hiroshi Ishiguro. As many of you may know, Professor Hiroshi Ishiguro is the father of the Geminoid. The Geminoid is the human twin of the human person. So Hiroshi Ishiguro built a robot which is a copy of himself, and this robot is a copy of a Japanese actress. And we had a kind of theater performance in Palermo when on stage there was the Geminoid F and the real actress interacting each other in a theater setting. We also had some experience in human-humanoid interaction by using this strange robot, which is a telenoid. The telenoid is a kind of robot which is not male, not female, not young, not old, and it is used for, it is a teleoperated robot, and it is employed for interaction between humans. So instead of using Skype, our idea is to use the telenoid. It's a kind of embodied Skype, an embodied version of Skype. Instead of Skype, you can touch it, you can hack it, and so on. So it's a kind of, I can say a sort of embodied version of telepresence. And we were involved in a project related with autism, with autistic people, and we use this telenoid for the interaction between autistic children and normal children. So we use this robot for the interaction between human and autistic, use the robot for the human interaction between human and human. And these are typical settings of our experiments when there was an autistic child, a normal child, and another child which controlled the robot. So there was an interaction between an autistic child, a normal child, and another normal child interacting with by means of this robot. We had also some experience by using these robots in interaction with people with amyotrophic lateral sclerosis. So patients that are completely locked in bed. And by using the EEG helmet, the locked-in people, this is one of my students, it's not a locked-in person. This is one of my students, and so the patient is able to move the robot by using the EEG helmet. This is a real settings with the impaired person. This is a person with ALS that interact with other guys by using the EEG helmet and the okay. We have some collaboration with Mostar University in Bosnia for a prosthetic leg, and we also had some interaction with our local conservatory music, and then we had this robot leading a string quartet, a real string quartet, and these experiments have some success, and in fact the Palermo Theatre, the Palermo Opera Theatre, get this performance before the real audience in their program. Okay, I would like now to pass. This was only for give you some idea of the project that we had in our report. So let's move to robot consciousness. I can say that speaking about consciousness and robotics has may lead to some progress. And in fact, as Dilbert says, what it's like to have no consciousness, and the robot could answer what it's like to be totally unimportant, and say, how do you like your consciousness now? So it could be a problematic for a robot to be conscious, of course. Okay, we started our interest into in consciousness by taking into account our cognitive architecture. Our cognitive architecture, we work since 1997 in our cognitive architecture. At the beginning, our cognitive architecture was tightly related with computer vision, and in fact there is a paper in Artificial Intelligence Journal describing the architecture. And the idea of our architecture is to have three different levels, three different areas, three different computational areas. There is the subconceptual area, which is the area generally related with the sensory data. And then we have the linguistic area, this one. The linguistic area is the area mostly related with the linguistic level. So, and between these two areas, the linguistic area and the subconceptual, the linguistic area we can say the symbolic area. Let's say symbolic. Between the symbolic area and the subconceptual area, which today would be considered a sub-symbolic, could be considered the neural level area, we hypothesize an intermediate level, the conceptual area, and in our view, the conceptual area is mostly related with the geometric aspects of the knowledge, as I said before. So, in our architecture, the subconceptual area is mostly related with the low-level processing of data coming from sensors, and we can say the neural network area. At the top, we have the symbolic area. In the current implementation of the symbolic area, we take into account some kind of hybrid formalism in knowledge representation tradition, maybe something like KL1 or semantic networks or whatever. Essentially, we use the semantic network because we have this distinction between terminological components and assertional component, which is useful for us. So, for example, the terminological component is something like this. An object this is a semantic network, so an hammer is a complex object. A complex object is an object. There could be complex object, simple object, and an hammer is made up by an head, is made up by an handle. The head is made up by a box shape, and the hammer is a cylinder shape. So this is the terminological part of our architecture. And as I said before, between these two areas, the symbolic area and the sub-symbolic area, we hypothesize a conceptual area. The idea of conceptual area is based on what is called the conceptual spaces, introduced in 2000 by Peter Jardenfors. Peter Jardenfors is originally is a philosopher from the University of Lund. We had some kind of tight collaboration with Peter Jardenfors. The conceptual space is a kind of metric space. It's a metric space whose dimensions are tightly related with sensory quantities. So in the conceptual area, the reasoning is a kind of geometrical reasoning. So we have the subsymbolic reasoning in term neural network, the symbolic reasoning, which is the highest level, and in intermediate geometric reasoning. So this is the overview of our architecture. So the conceptual area, we can have a space related to taste, for example, a space related to color, the color spindle, for example, a space related to space, and so on. So the color spindle, for example, is a kind of space. So if we reason about color by taking into account color spindle, we are reasoning about colors by using geometrical entities. It's interesting to note that very recently in the literature there is some interest into this fact of reasoning about things by taking into account geometrical reasoning. So, for example, if we have this scene made up by a hammer, a tennis ball, and a computer mouse, those pictures are taken from my 1997 paper, and you may recognize the fact that the computer mouse is very, very old. So today, no one uses this kind of computer mouse. So if we have this very simple scene, we can reconstruct the scene by taking into account some kind of geometrical entities. We use this kind of geometrical entities, which are named superquadrics. The superquadrics are geometrical entities generated by the quadric by taking into account some sort of parameters that are able to change the shape of the quadric. So all these elements are generated by the same superquadric by changing some shape parameters. And in fact, we can also have the hammer reconstructed in terms of the superquadrics, the computer mouse and the ball. They are approximated by using this kind of superquadrics, of elongated superquadrics. So we start from these scenes. Our computer vision system is able to estimate the superquadrics that better approximate this kind of scene. And this is interesting because we can ground the symbolic entities at the symbolic level in terms of superquadrics and then in terms of points in our conceptual space, because each superquadric may be considered as a point in our conceptual space. So if you consider the vector of all the parameters of a superquadric, it is a point in our conceptual space. So each point in this intermediate space represents a superquadric. And then, if we have the hammer is made up by two superquadrics, and then it's made up by 2 points in this intermediate level. So, at the symbolic level, we have this semantic network, the hammer is made up by a cylinder and a box, but each entity is grounded into the conceptual space. So, the cylinder corresponds to a point in this space, the box is a point in this space, and so this is the description at the symbolic level in terms of the assertion at the symbolic level. So we have the subsymbolic space, the subsymbolic level that generates the superquadrics describing the hammer, and then we have the symbolic level. So I don't know if it's clear. We have the subsymbolic level, the intermediate level, which is this one, and the symbolic level. The symbolic level is grounded into this intermediate. In order to generate assertion in our architecture, we use a very simple kind of Fox attention. So imagine that you see a scene, you estimate all the entities in a scene by means of superquadrics, and you have a lot of points. How do you, from these points, how do you generate the assertion? Because we had a lot of points, a lot of superquadrics. And so we need some kind of Fox attention. We have 2 modalities of our Fox attention. The associative expectation and the linguistic expectation. So, take into account an example of linguistic expectation. The linguistic expectation, the idea of linguistic expectation is this one. If the system sees something which might be similar to a hammer handle, so if the system sees something which is something like this, a cylinder which may be an hammer handle, so taking into account the definition of the hammer, then there is another superquadrix which is the hammer handle, the hammer handle. So the system recognizes a cylinder-shaped object. The focus of attention generates the fact that the cylinder-shaped object may be the hammer handle, and then it looks for a box-shaped object which can be the hammer handle. And so the system recognizes an hammer, and recognizes that this is the hammer handle, this is the hammer handle, and this one is the hammer handle. So this is a kind of linguistic expectation. I see something which may be part of an object that the system knows. So for example, a table, you may see an object which could be a part of the table, then I look for the other part of the table. So this is the linguistic expectation. The associative expectation, instead, is based on some kind of association which is related not to something which is not to any kind of definition, but to the learn. So the system learns that when there is an hammer, there is, for some reason, there is a box. Then the system learns this kind of association, and then when the system recognizes the hammer, then it looks for the box. So it's typical in the scene, in this kind of scene, have the hammer and the box. And so when the system recognizes the hammer, then it looks for the box. And so the focus of attention is driven by this kind of expectation. So it sees an object and it looks for other part of the object. It looks for the expectation. So these two kinds of focus of attention generate the kind of gazing exercise. It's not real gazing, but it's an exploration in this conceptual space. And then exploration by exploration, it generates all the assertions related to the scene. So this is a very fast overview of the static part of our system. Now let's take into account the dynamic scene. So this is for the static scene. For the dynamic scene, we have a kind of similar aspects. The dynamic scene is described into many other papers. I may suggest Artificial Intelligence in 2000, and where the role of we take into account a moving superquadric. So while in the static scene, each point in our conceptual space was a static superquadric, in the kind of the dynamic scene now, each point in a conceptual space is a moving superquadric. So we take the superquadric, we move the superquadric, and we analyze the Fourier transform of this movement, for example. So we take into account the Fourier transform, the Fourier transform of the move. We should take a principal component or whatever, but we take into account the movement of the superquadric. So each point of this new space, so we pass from the static to the dynamic space. Now each point in this dynamic space is a superquadric along with its own movement. So it is a moving superquadric because the vector takes into account the shape of the superquadric and the motion of the superquadric. So we consider the moving superquadric as points in this space. So each point is a moving superquadric. And so we may distinguish between situation and actions. A situation, in our view, is a situation. Let's take into account two balls in a billiard, two moving balls in a billiard. So each one of the balls have a kind of regular motions. This is a situation in which there are 2 points corresponding to 2 moving balls. So they go, they move. At some point, it may happen that these two balls may collide, there is a collision, and so the two balls change their motion states. So there is an action. An action corresponds to a kind of scattering of points in the conceptual space. So the two balls have two state of motion, there is a kind of collision, and then they change their motion state. And this is an action, where there is a change of movements in this conceptual space. We also have, and we also take into account the attention in this framework, and we have two different attention. I cannot enter into the details, but we have an attention when the robots are in a situations, when the scene, when the robots look at a scene with to say where there was the two balls moving, and there is also a diachronic attention along the time. But I don't enter into the details. So this is a kind of terminological component in this case, and we have the composite motion. We have the action of seizing, for example. Seizing is an action. Seize as a parser motion is made up by an arm approach and a grasp. Arm approach is a kind of stretch out, and so on. So this is the description of the actions of the situation at the symbolic level. So, for example, let's consider there are two people, A and B. A seizes an object, and so it moves the forearm, and at the first row are the sequence of photos, and in the lower row you can see the superquadric recognition of the scene. And then, as I say, as in the static case, we may consider the grounding of the action. So the action of seizing is made up by an arm approach, is made up by a grasp. The arm approach means upper arm stretching, forearm stretching, and all these actions correspond, the action and situations corresponds to points in this intermediate. We may also take into account, okay, those are the assertions generated in this plan. We may consider some more complicated action, which there is A that says in the object and pass to B, for example. And this is a kind of diachronic situation in which something happens from time to time. Okay, so we also have the linguistic attention, associative attention, and so on. So let's now consider let's now pass into the idea of self-consciousness. So our idea is that self-consciousness and theory of mind have something in common. So we like the idea that the theory of mind and self-consciousness evolve into humans at the same time. So the theory of mind means that that when I speak to another guy, I may imagine what the other guy is thinking, what is his background, what is his culture, what is her culture, background, and so on. And in fact, if I don't have a theory of mind of the other guys, it is impossible for me to interact with the other guys. And so, for us, self-consciousness is related with the theory of mind. It's a kind of theory of mind of themselves. So I have a theory of mind of myself. And so, taking into account this idea, so I have a model of myself, in some sense. We made some work into the theory of mind of the robot. So, for example, these are some experiments made up by in our laboratory by studying the intention of another person and representing by means of a conceptual space. So this is a person moving the arm, and the robot is able to look at the arm, at the movements of the guy, and it's able to understand the movement of the guy and to replicate the action. So in this case, self-consciousness is the robot that looks at itself. So the robot, instead of looking at another guys, instead of trying to understand the intention of the other guys, the robot look at itself and tries to understand its own intention. So as the robot is looking itself from the outside. So we have the conceptual space of the robot, which is this one, the lower part. And we have another conceptual space that look at the conceptual space at the lower level. So there is the normal conceptual level of the robot and another higher order conceptual space that look at itself. So the robot is looking at itself as from the outside. This is the idea. And then we may consider the self by taking into account this idea. So the robot is looking at itself, and then the robot is looking at itself, which is looking at itself, and so on. So we made higher order perception. So we made lower order perception. I'm looking at myself. So as I'm looking at myself, I'm thinking about myself in some sense. I'm thinking about myself, and so on and so forth. So this is the idea of self-consciousness. So I'm interacting with myself as I'm interacting with another guy. So I'm interacting with another guy, so I have some idea of what the other guy is doing and trying to take into account what the other guy is doing, and I'm looking at myself. Some of these ideas, we are taking into account this idea to consider self-conscious, the relationship between self-consciousness and robot trust. So consider a simple task to lay out a table for dinner, for example. If a team of people and a robot, they have to lay out a table for a dinner, I can do something by myself. I can delegate something to another, to the robot, and so on. So it is a kind of teammate. So if a robot has a kind of self-consciousness, so is able to say, I can do it, I cannot do it, I'm not able to do it, and so on. So it's this very simple kind of self-consciousness. So if I say to a robot, pick up this object, and the robot could respond, no, I'm not able to pick up this object because it's too fragile for my hands, for example, or because it's too high and I'm not able to grasp it, and so on and so forth. Or if the robot does not perform the task properly, but is able to explain why it failed, for example. So the robot pick up an object and the object broke for some reason. The robot should be able to say, yes, I broke the object because so and so. This is some simple experiment of self-consciousness, because the robot in some sense justifies itself. So it's able to look at itself from the outside, and so it could be able to justify itself. So so we are investigating on the fact if this kind of self-consciousness could be useful for trusting. So for example, the problems are related with violation of trust and the recovery of trust. So all we know that when there is a violation of trust, it's very difficult to recover the trust. So it can be that using self-conscious, so the robot is able to justify itself, and this could be useful for recovering